I'd like to welcome you all to the new RAS webinar. And my name is Nikola Vesinovic. I'm at Technical University of Dresden in Germany. And we have a pleasure after a break to restart RAS webinars. And we are happy to have two speakers talking on a hot topic of LIDAR or LIDAR for railroads, and represented by Daniel and Marty. So they'll give us a bit of a background on mathematics as well as the use cases, how it's seen for railways. And when it comes to Daniel, he has been with object computing and is an expert on LIDAR topic. And Marty is a long-time member of RAS and informs and basically provides his expertise to various industries and various companies in railway domain, and we can give them the word just in a second. So on some important information, we record this video. If you have any questions during the presentation, please write them in the chat. We will bring them up to Marty and Daniel right after, and I invite you to enjoy the ride, and I give the word to Daniel and Marty.
Nikola, thank you. Thank you to you and to Andrea and to the entire rail application section leadership for the opportunity to speak to you today. Nikola, you're correct that I have been associated to Informs and to the rail application section ever since I was a graduate student at MIT, and the man responsible for my introduction to Informs is in today's session. Thank you, Carl Martland, for that. And it's really great to be back in front of this group. So I spent approximately 25 years working for railroad companies and became an independent consultant in 2021. And the good fortune of that for me was that I was able to be introduced to companies and individuals who are making technical progress towards applications of advanced methods in railroads. And one of the most important partnerships to me in my consulting practice is with Object Computing, who is developing multiple AI-driven and other advanced analytic use cases that are specific to railroads. The one that we're going to discuss today is usage of LIDAR for multiple methods of maintenance of way, health monitoring, and maintenance. And so after a brief introduction here, I will turn the stage over to my colleague, Daniel Rusinek, to speak on the details of how one goes from the initial sensed data that is LIDAR to information that is usable by railroads in right-of-way maintenance. So let's go ahead into this. And we have a lot of material to cover. And so we will each be monitoring each other's chat, and we will have time for questions at the end of the presentation material here. So Daniel, go ahead and advance the slide. Yep. Okay. So we're going to start out with a little bit of context here, because only recently has LIDAR data become prevalent enough within the industry for us to consider the techniques and the cases that we're going to be able to discuss today. And so we're going to talk about what developments have occurred that makes LIDAR more available and less expensive than it has in the past. Then Daniel will give the real, important body of this presentation in terms of how one goes from the initial sensed data to understanding how it fits and what it means in the railroad context. And then we'll come back over to me and I'll discuss the use cases and the sources of value that come from those cases. And then we'll take your questions. So you're going to hear Daniel talk in very easygoing and conversational terms, almost casually, about stuff that is actually very technically challenging. And so don't be fooled by that. He has got impressive expertise in this area, and I hope it will come out to you during his part of this material. Let's advance the slide and keep going. Okay. So the broad context for why this has come to be a time to realize value in railroads is that the availability of LIDAR has really improved over the past decade or so. We have had uses of LIDAR and collection methods for LIDAR in railroads for some time. And you can see, the picture on the left is a purpose-built device that is collecting LIDAR for, typically a single use case provided by a single vendor, and so the railroads did not have the internal processing capability to go from point clouds to insights because the data was not in their hands. And so gradually, LIDAR has been democratized to a point where, as you can see in the image on the right, railroads can collect LIDAR data in train without separately occupying the track with additional vehicles and disallowing the movement of trains at the same time. So we don't specifically endorse any particular supplier or method for the capture of LIDAR data, but we would observe that railroads have their hands on LIDAR data in much greater quantities than they ever have. And so it's time to realize the value from that. All right, let's go ahead. All right. Now, at this point, Daniel will commence, and we will talk about the math that is behind processing LIDAR data. Take it away, Daniel. Thank you.
Hi, everyone. My name is Daniel. I'm an employee of Object Computing, and thank you, Marty, for the introduction. So let's get started. We're going to talk a bit about georeferencing data, which is essentially just, taking some data that's in a coordinate system of, just a scanner and locating ourselves on the Earth. How the Earth is subdivided, you have to subdivide it in lots of different zones, and there's lots of different ways of projecting, a round surface onto a map and being able to locate yourself and make use of that information. And then we're going to talk about processing the point cloud. So there are lots of different methods, but one of the main ones that I guess when LIDAR was first being used, mostly on airplanes, but also now when they put it on the back of trains. You really require three components. You need the actual LIDAR instrument itself, of course. You can see it right here. You need a GPS, which you can see is, at least in this particular one, is on top. I don't know if this is necessarily what a lot of train companies use, but this is a pretty typical what I used in grad school and stuff. You do need to actually keep track of the distance between these two because they're different reference frames. So you have to know how where the GPS is attached, and you have to keep very good measurement of all that. And then you also need what's called an inertial mass unit. And it's pretty much just a series of gyroscopes and accelerometers. And those are used because they can track the pitch, roll, and yaw of whatever moving platform you're on. And those can essentially help keep your GPS more accurate, because GPS really if you really want an accurate position with the GPS, it typically actually requires you to be stationary. So if you're on a moving platform, you want to, combine things. And so a big word you're going to probably hear a lot, and probably more in the future, is this concept of sensor fusion. So it's not just the LIDAR; it's really a system. So I have a picture here of an aerial LIDAR, just because that's what's been used for a lot longer, since like the 80s. And I think it's a little more easy to visualize. But for a terrestrial LIDAR or anything on a train, it's the same concept. But there are two types of LIDARs that you'll probably encounter. There's a full waveform LIDAR. That's mostly in academia and government agencies. You're probably not going to run into that. In commercial spaces, you're probably going to see a discrete LIDAR. And so when you shoot a LIDAR out in the plane, in this case, the laser beam does diffuse out, and when whatever area it covers when it hits the ground is called the laser footprint, and that kind of defines like the boundary of how much accuracy you can get. As the laser beam travels down, the light beams, they do actually travel through, holes and gaps in the trees. And I'm sure you've heard in like archaeology, maybe you've heard that they use LIDAR. They can see through tree canopies and things of that nature. And the way that really works is, so whenever the LIDAR hits an object, it returns laser energy back to the instrument. And when a certain amount, that amount of energy goes over some threshold, then it records a point. So you can have, we call these returns, because the energy is returning, the light energy is returning. So, you can have your first return, which is, in this case, would be your tree canopies. And then you have your last return, which we assume is the ground. And that can be very useful because then we can use that to essentially like wipe away tree canopies and structures and things. And we can see like they've discovered faults like that. They've discovered old like ancient cities like that, like hidden by trees. So that's just kind of general how this works. And then talking about GPS, there are currently 31 operational satellites. You'll typically see about 6 to 11, but that really depends on where you are, how many buildings are around you, and a lot of obstructions. But you'll typically see 6 to 11, more the better. You need a minimum of 4 for a position, but really you need more. But 4 is the absolute minimum. But you're not going to get a very accurate measurement off of that unless, again, you have your GPS stationary. And so on that note, and then here you can see this is, you're essentially triangulating yourself on the planet by using different satellites. And the satellites actually measure the distance they are from the antenna by just timing how long the signal takes. And so you have to have very accurate atomic clocks on all of the satellites. You have to account for atmospheric interference of the signal. You need to account for space-time curvature. You need to have, so even like a tiny fraction of a second will, give you a position that could be off by several meters at least. Other sources of error in GPS is, again, atmospheric noise, what's called multipathing. So looking at this picture right here, multipathing is, see right here, the signal's hitting the ground first and then going to the receiver. Well, then, so that's actually taking slightly longer. The receiver doesn't know that. It just sees that it took longer. So that can actually greatly affect your position. There are different codes that are used. I'm not going to go into the details too much, but if you're interested, feel free to contact me later, or I'll be here a little bit afterwards and we can talk about that. But there are codes that are used for civilians, and then there's some that are reserved only for the military. Obviously, the military ones are incredibly accurate, and the military also has the ability to turn off GPS accuracy in certain areas if they're like doing drills or something like that. So that can all be something that affects your errors, rounding errors and obstructions. So one big issue, at least in urban environments, is what's known as urban canyons. So again, you can get issues when you have buildings like this, and so you can get large multipath errors. There are a few ways to correct for this. You can, again, leave your GPS in a location for a longer period of time. It'll start averaging. But, if you're on a moving platform, that is impossible. Another possibility is to use a higher quality antenna, that they have certain structures built in to block out sources of interference. Avoid obstructions is really your best bet, but that's not always possible. You can also block signals that are coming from low elevations, because you're like, well, that's not right. Or again, combine your sensors, sensor fusion. So I'm going to keep coming back to that. So for example, you might want to combine with an inertial mass unit to help make your measurements more accurate. There are a lot of ways to combine these, a lot of different algorithms, but one that I've learned about recently that I think is very powerful is called a Kalman filter. And this is an iterative mathematical process that uses a set of equations and consecutive data inputs to quickly estimate the value, position, velocity of an object being measured, and measure really any quantity that you in time that has some error, that you have a predicted value of what you think that error is going to be. And when the measure value contains unpredicted or random error, uncertainty, or variation. The main, I guess the magic of this is in the Kalman gain, which is the error in your estimate divided by the error in your estimate plus the error in your measurement, which pretty much means that if you have a large error in your estimate, if your error in your measurement is small compared to your error in your estimate, this is going to be close to 1. And since it's going to be close to 1, this difference here, your measurement versus your estimate, you're essentially saying that you are trusting your measurement. So put more weight on the measurement. So obviously this is going to be a larger number. So when you do your new estimate, your estimate plus a much larger number here of your measurement minus your estimate. If your common gain is small, however, it's pretty much saying that your estimates are becoming stable. So start putting less and less emphasis on the measurement. And there's a whole process here. I'm not going to go through all this, but I can definitely direct you to some literature. And you can take a whole semester course on this. But the process pretty much goes where you have an original error estimate and you kind of just guess on that. And you calculate you get your error in your data. So you calculate a new estimate, then you add some noise to it. You look at how much uncertainty you have, you pass it through your common gain. So initial state, and you calculate a covariance matrix, and that's just kind of getting things like this U sub k is what we call your control variable matrix. So essentially it's forces that control the movement of that object. So gravity, for example, this W sub k is your noise matrix. This Q sub k is process noise covariance matrix. So again, that's just looking at how much noise you have from the process. Then you pass it through your common gain. So you update with a new measurement with your noise, your common gain, which we already went over. And then you update with the error in your process. And so then you basically repeat until you start getting to where your measurements are very accurate according to your common gain, and you will then converge on the correct answer. It's all going to be on the test, by the way. So anyways, moving on, obviously, I'm sure if anyone's tried wrapping a piece of paper around a basketball or any sphere, you can't, not without squishing it somewhere. So things are always going to be distorted. There's a lot of different projections, but two main ones that you may or may not have heard of. This one's called the Mercator projection. I'm sure a lot of you have seen this map, and it's ridiculousness of like Greenland being the size of Africa and Europe being the size of South America. This preserves shapes, but it doesn't preserve sizes. However, because even though your topology of this, it's a cylinder, locally geometry is Euclidean, and so you get straight lines of bearing. So that's why it was used originally, because it's good for navigating. Another projection is called a Lambert conformal conic projection, and it's the same thing, but you're projecting onto a cone. If you can imagine, any typical map of the United States uses this projection. And again, conformal just means that it preserves shapes. And there are other ones that preserve size and not shape. I've never used them for anything, but they are a thing that exists. There are also a lot of different, so this is what's called state plane coordinate system. There's also universal transverse Mercator, which is basically this, but the zones are global. For this particular coordinate system, every state has multiple zones, so you need to know what state you're in. And depending on what state you're in, what the shape of the state is, like for example, Montana, you can see you probably want to use like a conic projection. It would fit better for that state. But like for Georgia, for example, you would want to use a Mercator projection because it fits more into that, like onto a cylinder. And something interesting point that Marty brought up to me yesterday actually was, with railroads, like what happens if you cross multiple zones? And I can't say that's an issue that has ever arisen much in my work. I vaguely ran into it in some work I was doing at NASA, and we never really came up with a good solution besides just you have to keep track of where you are, and when you cross the state boundary, you need to just make note of that and make that change. And so again, you need to make sure that you have multiple sensors like GPS, LIDAR, and keeping track of your position very accurately. And then when you're measuring elevation, so the Earth is not a perfect sphere. It's actually slightly squished, kind of like a tomato. There's another surface that's a mathematically defined surface of equal potential gravity. It's pretty much an estimate of mean sea level. It's called the geoid. And without getting too nitty gritty, pretty much you want to use a reference ellipsoid, so you have an ellipsoid that you use to about estimate the shape of the Earth, and you want to use a reference ellipsoid that fits the best into the geoid in the area that you're in. So for example, in the United States, you would want to use North American datum 1983, but like you don't want to use that if you were in, say, China or something like that, because it's the ellipsoid you use is going to fit well in some places to the geoid, but not. So you need to know where you are. And this right here is just there are hundreds of these markers all around the United States set by the National Geodetic Service. And these are used to define the North American datum. So when we survey, we usually survey with respect to these. And then we have our point cloud. So this is just a point cloud of, this is an aerial point cloud that was taken. But if you zoom in, you see there's really just a bunch of points. And really, these are essentially all GPS points. They're all relative to the receiver. So it's really important that you know where your receiver is, because the only thing that you know other than the position of the receiver is how long the laser took to reach a point and return. And then you can figure out the point relative to the receiver from there. So if the receiver position is off, then everything is off. So again, the GPS is incredibly important.
Daniel?
Yes?
One point, if you don't mind going back one more slide,
Sure.
The distinction between geoid height, ellipsoidal height, and orthometric
yes.
height, I think is good to
Yes.
cover.
Yes. So when you measure with your GPS, your elevation, you can't really get your elevation at this point P. You get your elevation either in what's called ellipsoidal height, which is relative to whichever ellipsoid you are using, and you set that on your receiver, or relative to mean sea level, which is geoid. So in the case of what we're working on right now at OCI is we actually have to try to transform to this local elevation. So we kind of have to take some measurements and there's some APIs, there's a USGS API, there's also the Google Elevation API, and that you can use to then transform to that actual local elevation. Because for train companies, for a lot of these freight companies, knowing how high vegetation or something else is above sea level isn't very useful to them. So, that's something that you need to take into account. Thank you, Marty. And as you can imagine, these files are huge. They're gigabytes each, at least. So one of the easiest ways to work with them is to grid them into evenly spaced raster pixelated images. So each grid, basically, you assign one elevation value to each pixel, and the pixel width and height are pretty much, so you want maybe 0.5 meter by 0.5 meter. So each pixel would represent 0.5 meter by 0.5 meter, or 1/3 of a meter by 1/3 of a meter. And that's a resolution that's set by the instrument. So like if you're using any satellite or anything like that, like Landsat, they'll always tell you what the resolution is on the images that they give you. And this is just a small little diagram to illustrate kind of one way to interpolate. It's the simplest one. It's just nearest neighbor. It's definitely not the most accurate, but it is the fastest. It's log n complexity, whereas a lot of the other methods end up being n² complexity or worse. Actually, I don't think you can get much worse than that. Yeah, so each pixel is your X resolution, and they don't have to be uniform. They can be different, but usually they're uniform. They're both the same. So 0.5 meter by 0.5 meter, 0.5 foot by 0.5 foot. And you pretty much overlay a grid. You define a point in the middle of that grid, and you search for, and these blue points are your LIDAR points. They're a lot more dense in real life, but you would look for what the nearest point is to the point that you want in the middle of that pixel, and then you assign the elevation from that point to that pixel. And the result.
One other thing, Daniel, about the past two slides here, right, is that for purposes of display, we have two-dimensional information. There are two-dimensional exhibits, but in fact, this is happening in 3 dimensions.
Yes. And you can estimate 3 dimensions because, you have an X resolution, a Y resolution, and then an elevation. So you can more or less estimate a volume for each pixel from there. So the result is either a digital elevation model. I got those mixed up, but yeah, digital elevation model and digital surface model. And you might sometimes hear digital terrain model. There isn't really any, the nomenclature isn't all that standard. But essentially, a digital elevation model is this brown line here. That's when we talked about returns earlier. It's when you just do that interpolation using those last returns. So you pretty much get a bare earth model, what everything will look like with no cover, no trees, no buildings. And that can be very useful for geologic studies. That can be very useful for probably for ballast management. And then if you use all the returns or only the first returns, or really all the returns, then you get a digital surface model, which is an estimation of the entire surface, including all of the trees. And for vegetation management, that's what you're going to want to go with. And then once you have this nice pixelated image, the reason it's so nice is because you can do, really great calculations like, here I just colored every pixel that was above 6 feet, since every pixel just has one elevation value. Every pixel is above 6 feet, color it green and show it in a map. And since you know the area, because you know the resolution, you can also get an estimation of area. And since you know the elevation, you can also estimate the volume if you want.
And Daniel, that was where northing and easting came in.
Oh, yes, yes. And yes, so yes, going back to, I guess I need to mention that. Yeah, so going back here, when things are done in any kind of a projected coordinate system, you have a point at the edge of, let's say you're in Georgia, you have a point here at the edge of your zone, and every point you get is really relative to that point. So it's a certain amount of feet east of this point and a certain amount of feet north of that point. So that's what we mean by northing and easting. Thank you.
And in the in this cloud, you can represent the scales relative to that point, or otherwise localize them somehow, so that users of the system can orient to where they're at. Not everybody's going to know where the reference points are, but it's an arithmetic transform to make your scale something that is accessible to a user.
Another point that's nice about using projected coordinate systems is since now you're in flat Euclidean geometry, you can do distance measurements using Euclidean distance, whereas if you were using geographic coordinate system, just latitude, longitude, you would need to use great circle distance, haversine distance, because you're no longer on a flat surface anymore. So that's another point. And you'll see both. It really just depends on what your client or whoever you're doing work for is using, or whatever your research entails, or whatever the data you have is in. So, you just need to be aware of that and, structure your data accordingly. And then just another cool use case, and there's a ton of them, but I thought this was a cool one. Since the elevation, we know that water is going to go in the path of least resistance, so we can calculate and create maps of where water is going to drain. We can simulate a certain amount of water is just going to pool in certain areas. So that is another use case that railroads are very interested in, because they can try to figure out where there might be pooling in the ballast somewhere that might cause some kind of structural damage underneath, because the LIDAR can't really see underneath any of the ballast or underneath any of the ties, but we can see the surface. And if we know there's pooling, then there's a good chance that there could be some damage underneath. Another point here. So this is what's called an unprotected crossing. So it has a crossblock, but it doesn't have any signals or anything else. So basically, if you're a car and you're stopped here and you don't see a train coming, you can go. So that being said, there needs to be clear line of sight for you, or else, it could cause an accident. The company could get sued, people will get hurt, people will die. So at least certain companies have decided to they have areas that they define around crossings, that they want these areas cleared so that there's a good line of sight. And so we'll just call that the compliant shape from here on out. And there's different specifications. Overall, though, main point here is that, the faster the train's going, the longer the shape needs to be along the track, because the car needs more time to see the train coming, because the train will take longer to stop. Excuse me. And so, yeah, we're calling that the compliant shape. And we have created a robust algorithm that can handle any 2D geometry. It can handle curvature in the track, as long as we're given some GPS locations along the track as the train's moving, so we know where the curvature is. So it really doesn't require much GPS surveying. You need the trained GPS, which you already have because you're surveying with the LIDAR. And as we talked earlier, that's really important to have that with the LIDAR. And we take GPS at the center point, the midpoint of the crossing, and then we have limits pretty much where the crossing and the road meet, and that's really just so we can estimate and we can determine the width of the road. And it's quick performance, it's log-in complexity, and yeah, so that's the algorithm that we've been using for that. And we can fit bending shapes. Here it is in Google Maps. And we also have other areas where like we'll have multiple shapes that overlap with each other, and we can handle all of these cases with that. And then we have recognizing objects. And this is what everybody wants to know about. And there's, again, tons of stuff, and I don't pretend to know all of them at all, but I am pretty familiar with a lot of the main algorithms that are being used. So like, for example, you can have supervised. So there are two, well, as you may or may not know, there's supervised and unsupervised learning. Supervised meaning you need to provide a training set. So essentially you need to give the algorithm what the answers are, the questions to like what you want, like what is this, and give it the answers. We'll tell it what it is, and it starts to figure out trends, and then hopefully converges on an answer, and then can start extrapolating that to data it hasn't seen. An example is one called semantic segmentation that uses the neural networks, specifically one called a UNet. Not a big deal, but that one pretty much takes pixels or 3D pixels of voxels that you derive from the LIDAR, and it can start to classify those into different classes of like people, like that's a tree class, that's a road class, that's a car class. And so that's one method. There are also unsupervised methods such as principal component analysis. You can use this to determine your where vegetation is, because vegetation, for example, will have on average more sparse point spacing than solid surfaces, because just the vegetation absorbs more of that laser light energy. And then there's another one called simultaneous localization and mapping, or SLAM. And that actually doesn't require, that can be done with just a LIDAR, although that's usually, as I've read, done on indoor situations, but it can be done outdoors as well. It does require that you have GPS locations of landmarks though, because it needs to start, it's also iterative, and it kind of corrects itself when it sees a landmark. It looks at the GPS location and it uses that to kind of start to locate itself and map its environment at the same time. And that's why it's called localization and mapping. Or you can cheat. And if you have GPS locations, like let's say you have the GPS location of the speed limit sign, and you, instead of having to try to identify the speed limit sign from a bunch of points, if you have the GPS, you can just tell an algorithm that, hey, when you are at this location, this is where it is. And you can start giving it the answers based on that. So again, just this concept of sensor fusion. And I think it's really important to use all the tools available to us. Here's just an example of a crossing. You can see all the wires, you can see the trees. Oh. Oops. That is not what I meant to do. There we go. And then here's another example, more from an aerial view. And then just here's another example of this compliant shape at another crossing. You can see here we have this road, Plum Tree Road here. So that's another case that we'd have to account for. And we use several APIs like the Google Road API to help manage these shapes and make sure that they fit the roads, and we have a good estimation of our location. We use the Python Shapely library to create this polygon. And ultimately, we estimate the volume, like I showed before with that picture where, I had the green pixels, and we estimate the volume inside the compliant shape of, for example, how much vegetation we might have. So if, we can mark how many pixels do we have above 6 feet within this compliant shape. And then that's ultimately the answer that we want to give to the corporate executives at these companies, because they have a lot of other things that they need to worry about. So the idea is that, we can automate a lot of this stuff, a lot of the science here and the physics, and they can get the answers they need quickly to make business decisions and ultimately hopefully save money and create better efficiency and better processes. And with that, I will give it back to you, Marty.
Daniel, thank you. So as I think you've been able to tell from Daniel's presentation, it takes quite a bit of startup to go from point cloud to understanding. But even, that is only kind of a midpoint in the journey to actually prompting business decision-making off of this information. And so this is an example of where you would take this further. And so we've been talking about the necessity of keeping crossings clear of obstructions for motorists for the sake of the safety of both the railroad and the motorists. And so, okay, a LIDAR survey, whether that is in an independent rail-bound vehicle or whether it's taken in train, will generate a list of crossings that are traversed in the course of doing the survey. And those then can be ranked based on, application of the ranking methods that Daniel mentioned and the volumetric calculations or identification of the obstructions that occurs further upstream in the information. So, okay, so then you have, or any railroad has choices to make, which is how to package the crossings that are identified as needing action and distribute those to crews that would take that action and report back that the obstruction was cleared. And this is, of course, after separating out non-actionable obstructions from actionable obstructions. And so, ultimately what we're shooting for is to have all of this processing inserted into a business process that previously was more manual and occurred less often. So, each railroad wants a little different view of how you would rank the crossings, group them, and assign them for action. But fundamentally, the necessity of keeping the crossings clear is what creates some common approaches at this stage, which is to plant these analytics inside the business process. Daniel, let's move to the next one here. Okay, so we have been talking about the sightlines case, right? The task of keeping crossing sightlines open for motorists, because it is one of the best developed ones that we have, but we also are at work on a number of others. And so I'm just going to tick through those quickly in the rest of this presentation. So if you can identify vegetation blocking sightlines at crossings, you can also identify it encroaching on the railroad clearance envelope, even if you're not at a crossing. So vegetation grows, slopes move, rainfall occurs. And so the clearances that you have on your railroad, so, to prevent trains striking things that are, next to the tracks, aren't guaranteed. They have to be resurveyed periodically, and vegetation is only one thing that can encroach on the railroad right-of-way. Another big one is sagging wires. And so when a wire was installed above the track, there may have been plenty of clearance, but very gradual swaying in the pole and its foundation that may have happened because of seismic events or settlement of the ground in which the foundation sits will cause the wire to sag. And so if the sag puts the wire at close to the top of the height of railroad equipment, then you would want to know that. And you could send out a separate survey, but if your railroad regularly takes LIDAR, that would be probably the most frequent and effective way to accomplish that. And so maintaining the clearance envelope, is sort of a super case because it encompasses not only encroachments from vegetation, but encroachments from other movement of the the environment around the railroad. And then the railroad track itself is not static. Curves will walk, if you will, they'll push out, over time with tonnage, especially if the ballast section doesn't sufficiently hold the track in the curve, or if the super elevation and the prevailing speed of trains is unsynchronized somehow. So it's not just the environment around railroad tracks that moves, it is also the railroad tracks that move themselves in minute but sometimes important measures. Daniel also mentioned ballast, right? And so, railroads dump millions of tons of ballast on the railroad rights of way and tamp them in, tamp the ballast in under the ties every year. It's really a critical element of maintaining the rail subgrade and the surface conditions. And that's for good drainage so that the ballast remains supportive of the ties, even as trains pass across the rail route every day. And so making sure that the drainage ways adjacent to railroad rights of way are always kept clear, and that opportunities for water to pool and infiltrate the subgrade are addressed is an extension case from the ballast management case. Lastly, and as Daniel said, one of the things that's important in these other cases is to distinguish what is actionable from what is not actionable. Part of that is fitting the railroad right-of-way boundaries across the LIDAR survey at all times, because railroad right-of-way boundaries are not static. Sometimes they're 100 feet wide, sometimes 50, sometimes 200. And, if an encroachment is actually just on the other side of what the railroad has authority to address, then you would have to make that distinction. But the other thing is you're going to find a lot of common and repetitive objects in the railroad right-of-way. And you need to identify them and make sure that you don't send a crew out to remediate something that has to stay there, such as a signal mast, crossing protection devices, signal bungalows, propane tanks for switch heaters, the dual control switch machines themselves, and other common appurtenances in the railroad right-of-way. Now, one last thing that you would like to know is if something has moved from its understood location in the railroad's asset database. And so the final case that is supportable using LIDAR is whether the assets are where you think they are, and whether anything new has appeared that hasn't been recorded, or anything has disappeared that still needs to be there. All right, let's move ahead, Daniel. All right. So in terms of how railroads derive value from this information, there are both qualitative and quantitative ways to understand that value. And so across the top is, our take on where the value comes from by processing the LIDAR data in the cases that we've been talking about. In all cases, you have the ability to understand something that may have changed, or the condition as it stands if you didn't previously know. In 5 out of the 7 cases, that has a direct application back to the safety of the rail right-of-way, of train operations, and of motorists and pedestrians that may be using railroad crossings or otherwise involved in the railroad right-of-way. Or in the case of drainage and the possibility that pooled water may erode the supportiveness of railroad subgrade, there's a safety aspect to that as well. Railroads today are manually surveying a substantial number of the open questions that we propose to solve with LIDAR data today. And so there's a potential for cost reduction over time by the replacement of manual work with this data processing. And then finally, with the information derived from this, you have the ability to better deploy your personnel and monetary resources in your equipment to achieve the highest possible maintenance state of the railroad. So this is idealized to some degree, but I do believe in the sources of value, and that together, maybe not separately, but together, they provide a basis, to actually undertake the challenge of railroads processing their LIDAR data and taking it at such intervals that your information remains current. All right, let's move ahead, Daniel. So for the optimization professionals, who are part of this meeting, I did want to give a nod to optimization formed problems. And so that's why we're going to go back and revisit the ballast case a little bit here, because much of the rest of this presentation is focused on mathematical techniques other than optimization. But in order to fully realize the value of what you would detect in the ballast section, really optimization is necessary here. And so when you apply your LIDAR survey and you measure the ballast section in 3 dimensions, one of the things that you find is you take cross-sectional areas and you compare it against the ideal profile, is that you will have areas where the ballast has subsided or fallen away from a supportive position in the subgrade. Okay, and so ballast needs to be replaced. In other cases, you have approximately the right amount of ballast, but it is misshapen somehow, and that's also compromising the supportiveness of the ballast of the ties. And then lastly, you may have areas of surplus where the ballast is mounted up because it was laid too thickly the first time, or whatever reason, there was spot maintenance that left you with a surplus of ballast. And so the ability to offset deficits with surpluses locally is also provided by a piece of equipment called a ballast distribution system. And so as you take a route's worth of LIDAR survey of the ballast section, you then have to apply the correct prescription. Is it simply to add rock because you have too little? Is it to surface the track but with no net addition of rock? Or is it to displace ballast linearly across the track? Then you got a set of constraints. You can't do everything you want and nothing is free. And then you've got a bunch of parameters that would further inform how you would set up an optimization model to give you a ballast plan that is derived from the sensed information from the LIDAR system. All right, Daniel, let's go ahead here. All right, so the assets involved, you guys know I love rare earth equipment, and so I chose to include some here, right? And so you can, I think, tell that the cost, the complexity, the independence of each of these pieces of equipment is somewhat different, which gives you some challenge in making this planning decision. Railroads do it today basically through expertise alone, and that's something that cannot be dismissed in a production system that would that would give guidance to railroad experts. But this is what we got. This is the assets that we have to deploy to ballast management. And this doesn't even fully cover it, right? Because you also have shoulder ballast cleaners and undercutters that are more targeted towards removing fouled ballast conditions and replacing the fouled ballast with clean ballast, which can then become fully supportive of the track. All right, one more. Okay, so this brings us to Q&A time. And thank you all for your attention. We hope you've stored up some questions, even if we don't see them in the chat now. So, to wrap this all up, railroads have an opportunity that they did not used to have with the frequent comprehensive collection of LIDAR without incurring significant expense or track occupancy. So multiple approaches, whether they are hand assembled by railroads or purchased in whole from vendors, allow the collection of LIDAR in quantities that would make its use in these cases viable. So, all right, in order to derive this value, you need really two things, right? So you need to understand the nuances of the collection system, the GPS environment in which the collection exists, how to fuse the sensors and augment your GPS with inertial mass units. And this is particularly important in GPS denied environments such as tunnels. And thinking about the systems outside of North America, in Europe primarily, there's tremendous tunneling that is part of the rail infrastructure. And so having a solution that works in tunnels is crucial there. So, okay, so you have to know what to do with the data and how to interpret it. And then, you have to know the cases. And so, this is rarely equally strong in the same individual or company. And so working in partnership between the people who can speak to the domain and the people who can speak to the techniques really is a good way to move forward. So developing any of these cases individually, might not provide the return necessary, but developing all of them, there is definitely some economies that are captured, because once you have the ability to identify objects in LIDAR and take measurements, in the three-dimensional space, then you have the ability to fully develop the cases with the initial investment covered. All right, so that brings us to the end of this material. Thank you. And what questions do you have?
Yeah, thank you so much, Marty and Daniel, for this quite interesting presentation. So we have one question already coming up from Lynn, and it is, basically he's asking about some case studies for working with railway construction companies or maintenance companies. So is that something that you have been testing already, or where are you with it?
Yes. So our approach so far has been to collaborate with railroad operators. And the reason for that is that the operators now are capable of engineering or purchasing the sensor systems and having the data in their possession, ownership, and control. So it is possible to work with a contractor or vendor who would be invited onto the railroad right-of-way to take the LIDAR data and to engineer these cases for a supplier rather than for an operator. In North America, we think that the value is most readily achieved by the large railroads themselves, but it would not prevent us from basically offering the same collaboration capability with a vendor. Now, the challenge here is that if you're going to occupy the track with a separate dedicated sensing system to take the LIDAR, and you're taking the track out of service to do that, that's problematic, and it imposes costs on the railroad network in the form of, not being able to use that track for other purposes. So in order to survey an entire route, or really, an entire railroad network repetitively, so that you maintain the knowledge base for, the conditions and features that are found in the LIDAR, you probably can't afford to give the track time up for that purpose. You need to do it in train. And, that's another reason why we are collaborating with railroad operators. So the case studies that you were asking about, Lynn, as we said during the presentation, the sightlines case is the one that is best developed. And that's the one that was discussed in the University of Delaware Big Data in Rail Maintenance Conference in December. As you can see, we've made quite a bit of progress since then on these other cases, but we do not yet have published material on those. We expect to, but it's not ready yet.
And one kind of interesting side note about, we have to run the LIDAR. We can't be stopping and keeping trains from operating while we're surveying, is oftentimes we run into situations where there's maybe a stopped train on the other track, which actually creates some shadow zones and actually starts blocking some of the data. So that's may or may not be something that the companies care about, but we do keep track of that, and we're looking into ways to kind of manage to identify those and as an obstruction, and we can at least let our clients know that there's an obstruction here, and then I guess they can decide what kind of action they want to take there.
Daniel, thank you for pointing that out. And you're right. So the record in railroad databases of the most recent LIDAR survey needs to have a quality element of it as well, like was the LIDAR survey on this side of the sensor unobstructed, partially obstructed, and so on. And the same question could be asked and have a different answer on the other side of the track. So, really good call out there. Okay, so looks like there are several more questions.
Yeah, so maybe I can help the one with, from Coleman. Basically, it seems that you need some frequency of data collected. So have you thought about the minimal one that you would need, and how would that translate to the operator? Would you expect that every locomotive has LIDAR equipment, or every third, or one vehicle running through the network constantly? Do you have some ideas on that one?
Yeah, so let me take the first part of Coleman's question, ideal minimum frequency. My opinion is annual. And the reason is that vegetation has a growing season, and that ballast planning tends to be done also on an annual basis. So as railroads work in the fall to establish capital plans for the following year, to have a fresh survey that was taken within the last 12 months, corrected for what work has been planned and carried out, or planned but not yet carried out, is really what's necessary in order to provide what I think would be sufficiently current information for planners. So then the question about, really how many vehicles need to be equipped with LIDAR. It is the case that you can over-survey and undertake a lot of data processing that does not have incremental value, or doesn't have sufficient incremental value. And so how often you survey, and then the interval between your processed data, is really two separate questions. And one of the utilities that you might gain from a resurvey that is more frequent than you intend to use, because not enough has changed, is still the opportunity to unobstruct some of the obstructed areas, right? So if successive surveys do or don't have adjacent rail cars, then that's a way to fill in a gap that you might have had from your last survey.
And just to add on to what Marty said, it also kind of depends on what use case you're looking for. In this case, like if you're looking for vegetation, basically, if you take multiple scans, you can actually, and you have them in the same location, you can actually subtract from each other, and you can, get an estimation of, like, for example, how much vegetation has grown between scans. But areas, for example, in the northern United States, or in colder areas in the winter, you're not going to have a whole lot of vegetation growth. So that's just something to take into account. Whereas in the south, you're going to have vegetation growth pretty much all year round. So that's another consideration.
Yeah. Thank you, Daniel. And now I want to take Dave Hunt's question next. Can LIDAR be used to identify types of vegetation, or perhaps multiple readings can predict growth rates? The latter, yes, we think that is possible with, with frequent resurveys. I do think it's possible to do some modest extrapolation to be able to identify growth rates. Now, you can't necessarily identify it by type down to, sort of tree species, but you certainly can identify density. And that's an important, factor, because to the extent the density and growth are related, then you can at least derive some sort of insight from that. But both for David's question and for Mr. Provenzano's question, what's the main advantage of these LIDAR applications over camera-based systems? The data volume definitely is a factor here, right? Because of course you've got a 2D image which has some attributes to it at the pixel level, versus each LIDAR point having relatively compact attributes. But going back to Daniel's point about sensor fusion earlier, you've got a situation where these things work better together than separate. And so ideally, you would engineer a system where you've got the 3D representation in the abstract using LIDAR, and then you've got a contextual aid in the form of being able to reference the camera.
Adding on to what Marty said, I'm not sure if you can. I've never heard of being able to figure out the type of vegetation. I mean, you can get maybe a little bit, like if it's like a shrub or a large tree, but I recently learned that you actually, I don't know if you recall, I was mentioning that vegetation absorbs more of the laser energy. And so the average point spacing is slightly different. You can actually take that, and apparently the point spacing is different for healthy vegetation versus unhealthy vegetation. So you can actually tell whether vegetation is healthy or not. So, you might be able to tell what type. I'm not really sure. There's so much new research being done.
Thank you.
Okay, well, that's a quite interesting one, and maybe a short one on data. So you're collecting lots of data on your side, but then on the other, there has been plenty of researchers hungry for data. Is that something that you are hoping to feed and maybe provide some open data sets to encourage people coming up maybe with even new applications of this kind of data?
That's a good question, Nicola. And I would say first that we are not the collectors of this data, and therefore we're not the owners. We are the processors of it on behalf of the owners, which are railroad companies. So that would have to be a three-party discussion between ourselves and other researchers, academic institutions, and either the railroad company or another type of collector. So I'm not going to rule anything out, before seeing specifics. So I think there is the possibility of this leading to public insight and potentially, that type of representation in the future. But, really who's most important in making that decision is the owner of the LIDAR data.
Another point, this application, this cloud application that we're developing at Object Computing, we're developing this for a couple of railroad companies, but we really see huge potential in this, and we would like to eventually sell the solution, maybe even open source it for government institutions. And there is one source of public data that you might find interesting, though. It's called the 3DEP, just as 3DEP, all capitals. It's collected by the USGS. They pretty much collected high density terrestrial LIDAR for the whole United States. There isn't very good frequency, though. Like, for example, we were trying to use some to check some data, the accuracy of some of our data, and the only one we could find was 6 years old from what we had. So the frequency isn't great, but you can get some good, you can locate crossings in that data. They have the entire continental United States covered. But again, we would really like to, after figuring out all the cloud engineering aspects of this, which I'm not gonna lie has been a pain, we really would like to share this with as many people as we can once we engineer the solution or the final solution.
Okay,
Excellent.
well, it sounds, sorry, Marty, would you?
No, good. Thank you again for this opportunity, Nicola.
Okay,
yes, thank you very much.
I would like to thank for very fruitful discussion and presentation. And Marty and Daniel, thank you again. So basically what I would like to share with all of you, RAS is also hosting a rail planning conference. More details are in the chat. And this brings us to the end of this presentation. If you are willing to stay a bit longer to catch up with Marty and Daniel, they are available. So feel free to turn on your camera and say hi to them. Thanks a lot and have a great day.